Welcome to In the Loop, a New England Temperature Solutions podcast. In today's episode, Dominick DeLuca, president at NETS, will be interviewing Dan Bender. Dan is the Director of Sales for Control Concepts and has been in the heat treat industry since 1972. Without further ado, here is Dom and Dan helping you get in the loop.
Good morning. Welcome to today's podcast of In the Loop. I'm here with Dan Bender from Control Concepts. It probably should be called two old guys having a conversation, but we won't go there. It might offend people. But so Dan, you live in Pennsylvania?
I live in Pennsylvania, in the Pittsburgh area.
Tell us a little bit about yourself and where you live.
Well, I live in the east suburbs of Pittsburgh, which is about 25 miles from downtown Pittsburgh. I'm married, and I have 6 children, and I'm a proud grandfather of 10.
Right. So you talk about a big family event with how many people? 20 something?
When we all get together, there'll be 23 of us.
Nice.
Yeah.
Very nice. Must be fun around the table.
It can be fun. It can be challenging.
Noisy.
Noisy. Yes, definitely noisy.
Kids. Yeah. How old's your youngest grandchild?
The youngest grandchild is a year old, and the oldest one is 24.
Right. And your youngest baby is how old?
My son is 30. And
okay.
My oldest daughter is 50.
50, okay.
So there's a 20-year span.
Wow.
And incidentally, it's one marriage, one wife.
So you've been in this industry for a long time.
A long time, yeah.
Right. You're figuring that out. How many years have you been in?
I've been involved in this industry for 52 years.
52 years.
Yes.
Wow. So a lot has changed, right?
There have been a lot of changes, yeah.
Okay, so that was 1972?
1972.
Okay,
correct.
So 1972, you got your first job, you're driving to work, you got your little AM radio on in the car, and you're listening to the number one song of that year, which was American Pie by Don McLean, okay? So when you went and you saw that SCR in 1972, what did it look like?
It looked like an albatross. I didn't know what to think of it. It's big black heat sinks and this gray can, which basically was the electronics that fired the devices and so forth. Totally live. If it was 480 volts was right there for anyone to touch it and get zapped.
Touch safe?
No.
The opposite of touch safe?
The opposite of touch safe, it was hot. Basically, electrically hot. Yeah.
I remember those days. I worked in electronics early on in the 80s, and I remember they had these big capacitors that look like water bottles today, right? I mean, you don't see that. I don't see that anymore.
No. You had this big, it was an RC network. You had the caps, the big round caps that you had, and these big, tall cylinder resistors.
Mm-hmm.
It was kind of unusual stuff.
Yeah, weird. And you had to calibrate with pots.
Yes.
Right? So you had these big pots.
You had the big pots, which were gain in bias or zero in span, depending upon which technology you wanted. And you had to set them so that you set your zero when the unit turned on and set it for when it would be full on.
And then you're using a metal screwdriver.
Using a metal screwdriver.
Putting your hand in.
Yep, reaching over a hot heat sink. Yeah.
Wow, yeah. And I remember doing that, being probably at the beginning naive. Because you can't see electricity, but it's pretty scary. I mean, by today's standards.
By today's standard, it would be very scary, and it would be unsafe. It wouldn't be allowed. Yeah,
I mean, you think. I mean, I joke that the most scariest thing I did ever in my life was drive to Minnesota on my honeymoon without a cell phone. Right? Back then, things like, I mean, that's crazy. But back then, we didn't think about putting your hand in 480 volts with a big metal object that could have killed us.
Yeah, absolutely. You go into a cabinet, a metal enclosure. And you have all of these devices. You have, 6, 8 of them, and you're reaching over, and you're spending time adjusting each one. Yeah, it was a little scary.
Okay, and it was all analog, all probably 0 to 10 maybe inputs. 4
to 10, 4 to 20 was just coming along, but most of it was 4 to 10, or 4 to 20. There was some 2 to 12. Which was an old...
right. And it had 0 to 50 at some point, too. 0
to
50
millivolts.
Millivolts.
Yeah, and then you had manual potentiometers. You would have a 3 or 5K pot, so you would manually turn this thing on and off.
And I knew, because I'd worked on some of I started in '84 as a bench tech for Barbara Coleman temperature controller, and our devices were tied to that. And controllers back then were big and ugly and had tubes in them.
Mm-hmm.
Did these have tubes?
No, they didn't have tubes. They were solid state.
Okay.
As solid state would be considered then, yes. Yeah.
'Cause in 1980, I went to Rhode Island School of Electronics, which is gone, but in Providence, and they told me, we're going to skip the tube chapter. You're never going to see it. And one of my first jobs trying to fix a temperature controller, there was this thing on it, like, what is this? It was a tube. I had no idea what to do with it. So back then, things big, bulky. I mean, so the unit that's like this big, how many amps was it?
That big, let's say this, approximately this size is probably about 50 amps.
50 amps.
Yeah, because you didn't have what you have today, dual-sided cooling of pucks and that, so it was individual stuff. So the heat sinks were large, and they didn't use a lot of fans back then. Everything was natural convection cooled. So
this unit here is like half the size of that, and this is a couple hundred amps.
This is a couple hundred amps, and this would have been something of this size, this very size here. Probably, this is a three-phase unit, I think. Now, you're looking at a single-phase 50-amp analog unit that would be about that footprint.
Yeah. So it really come down in size.
Oh, significantly, yeah.
And so fast forward 42 years.
52 years.
My
Yeah.
goodness, 52 years. I was going to say I'm not even 52, but that's not true. 52 years, and what's the number one difference that you see in I mean, there's obviously some obvious ones, but what do you think is the number one difference between 52 years ago and today?
From an SCR technology
Yes.
thing,
Yeah.
it's obviously is the digital technology and the capabilities that you're able to do. Yes, you can communicate, you can do a lot of things. But for me, I would have to say one of the biggest things that I saw was change was the ability to look at devices, an SCR that's operating into a potentially short circuit, and the ability to eliminate or reduce the amount of nuisance fuse blowing. And that was a major problem with SCRs when they first came out. Depending on the application, you would blow fuses because of self-clearing faults. And the ability of digital technology to be able to sense those fault currents in a half cycle and be able to shut the unit down and set it so that it could come back on if it was self-clearing. And that was a big problem. And it led to a lot of misnomers that SCRs were not reliable.
Mm-hmm. And because changing fuses with just like a little spike is costly, time-consuming, would take hours sometimes.
It could, depending upon, well, first off, if the fuse blew, the unit is shut down. So if you're operating a furnace, the furnace is shutting down, it's cooling. Then do you have spare fuses available? How long does it take you to get them? Right. And remember now, we have a electrically hot piece of equipment, so you've got to have a mechanical disconnect. You've got to shut it down.
Right.
Now you got to find, make the connection, disconnect the fuses, take them out and put it in. Yeah, you're probably, the physical time just to replace the fuse was probably 15 minutes to a half an hour. And that's depending on, you had the fuses right there.
Right.
So, yeah, it would be a lot of downtime as a result.
You could
of
get
it.
the right person. If it's a union shop, it might be a little more difficult. You got to get get permission, get the
Sure.
person there. And then, having the fuse. And the other thing is you've got this furnace. A lot of the things we sell to are in the thousands of degrees, maybe 1,000, 2,000 degrees. And those things can't really drop temperature. You don't want them to drop temperature. Maybe lose production.
Oh, yeah, because a lot of them, if you look at it, if it's a, for example, if it's an atmosphere furnace that's on a conveyor, that's product that's coming out constantly. Well, you just shut down an entire production line when that goes. And that was an issue that we had to deal with. Yes, there was no question that from a mechanical contactor, an SCR could give you more precise control, but how reliable?
Good question. The SCR versus a contactor, right? So you've got the click, click, click Back in the day, it was all mercury contactors, probably no solid-state relays.
Or mechanical.
Really. Mechanical relays. So, now you come up with the SCR, which stands for?
Silicon Controlled Rectifier.
Right, and it gets confused with a saturable core reactor all the time.
Saturable core reactor.
It's a whole different story. Yeah. But talk to me about the two. Basically, you've got zero cross and phase angle fired. And while you're doing that, tell me what types of furnaces or ovens or whatever the zero cross would go on and phase angle fire.
Sure. Basically, what you're looking at when you're determining which method of firing that you're going to need is to look at what the actual resistance load is at. If you have, and you can usually look at this from temperature related. If it's under 1200 degrees Fahrenheit, then the resistance is probably constant. So it's a constant resistive load. It's not changing over time. So you can use zero voltage fired. And zero voltage fired is it's on for so many cycles, it's off for so many cycles. Okay? But it's constantly changing. And what I mean by constantly changing is that it's a variable change. As the load changes, it will change that timing. So you're not on a set fixed type of firing, where if you had a contactor, it's on, it's off. Well, with an SCR, you can turn it on, it stays on, and once it passes and goes through zero and commutates off, then you can be off, and then you reset the time. That's where the productivity came in, where an SCR could keep temperature a lot tighter.
And we're talking cycles, so we're talking 1/60th of a second.
1/60th of a second.
As opposed to a contactor, which is 10 seconds
Could
on.
be 10 seconds, yes.
Right. Which they couldn't go on. They couldn't turn on and off because they'd die. So you had to have a long cycle time, which meant it was like your house. You'd have a big hysteresis of temperature.
Yeah.
So I know selling heaters over the years that the zero cross, because it was so fast, and the phase angle fired increased the life of the heater significantly because it wasn't heating, cooling.
Right.
So tell me a little bit about why you'd use phase angle fired.
Phase angle fired, you start looking at, again, you can look at it from a temperature related. When you get to very high temperatures, then you get into more exotic type of heating elements where the resistance characteristics will change over time and temperature. And typically on a cold resistance, you're going to see an inrush of current. So you get this big slug of current. If you hit it with zero voltage fired, it's going to look like a short circuit, and you're going to shut it down. Phase angle does. It comes on for a portion of the cycle and gradually builds it. And as that resistance changes, it will modulate to where it will be turned full on. Another issue that comes into play with variable resistance loads is a lot of times the load voltage needed for the process is significantly lower than the line voltage coming in. So therefore, you're coming in with 480 volts. Your operating voltage might be somewhere between 80 and 200 volts. Now we got to put in a transformer. So now we're controlling a transformer in addition to the load. Zero voltage fired will not operate into that. You'll have a lot of other issues with that. So now, once again, you get back to you turn it on gradually, and the core of the transformer gets set to the point where it will not look like a short circuit. We can get into a whole lot more detail. But,
Right.
So those are the two. And again, you can usually determine that based on temperature because that's going to dictate the type of element and the characteristics of the element.
Right. Like I know a vacuum furnace is always a transformer.
Yes.
And it's always phase angle fired. So there's phase angle fired also talk about the temperature coefficient issue of heaters, where when you first turn them on, they're dead short, and the resistance changes drastically, and why we need phase angle fired for that.
Yeah. Well, as you said, when you first turn on, let's say you're nominally operating at, let's say, 100 amps. Okay, and that cold resistance when you first turn on, you could see 20 times that when you first turn on. So you would see a significant slug. So if you're using zero voltage fired, your nominal operating level is going to be 100 amps. But now when you take into that account that 20 times inrush, well, now for this thing to operate correctly, it's got to be 20 times that size. Well, you only need that for a short time period. So that's where phase angle comes in. It gradually lets it come up, and you put it in a device. This is where the digital technology starts to come in, where you have what is called a current limiter. So you can set the current limit so that you don't exceed the nameplate rating of the device that you have. And what that does is it alters the firing angle, allows it to come up a little further as the resistance changes to where it gets equilibrium.
And soft start, they call that soft start.
Soft start with current limit.
Current limiting, right.
Yeah.
So no matter what, wants to go to 10 million amps, it says, no, you're not going there.
We're not going there, and we won't go there until that resistance changes to the point where it's not drawing that excessive current.
Right. Perfect. And what kind of heaters have those issues?
Yeah, the most common one that you see at least in the furnace industry, is probably silicon carbide.
Okay.
And
so
that
like the I2R glow bars, stuff like that.
Glow bars, yeah. Glow bar is a trade name that I think it was originally was carborundum that came up with it, which now is I think that's where Canthal comes into play, without getting in. But that's where that came from. The other ones are molybdenum disilicide, or Moly D, as is often referred, and you find that a lot in the vacuum furnaces. Again, temperature ranges that you would be seeing these would be getting up into where you're almost to 3,000 degrees C, anywhere in that area. You'll see some tungsten. You'll see platinum, depending upon what the application is. So, and those are all variable resistive.
Okay, and those have to be phase angle fired.
Have to be phase angle fired.
So,
yes.
So then there are these heaters out there that over time change their resistance. Their resistance changes as they wear out.
Yes.
Right. So we have a feature that lets you monitor resistance.
That is correct.
Tell us a little bit about the power of that.
Well, first off, if in that type of an application, it has to be directly coupled. It cannot go through the transformer, because the SCR, it's looking at the transformer, not the actual load. So it has no way of determining what the resistance is. But you can measure, if you're directly coupled, we can sense and we can look at resistance of the element and change the in that case, you're using most of the time zero fired. So now you can change that on and off period based on how that resistance changes.
And when the resistance changes too much, they can't get the power they need.
Right.
So we have set points to say if your resistance changes, you can monitor it.
Yes.
And you should think about changing your heater before it decides to break and become zero resistance.
Yeah. It's
infinity.
It's another advantage of the digital technology that enables you to do that. So now you can do predictive maintenance. If you're looking at the resistance and you're seeing it's changing, and you know over past history, as this resistance changes to a certain level, that heating element's life is nearing its end. So instead of waiting till you have a downtime, you can now schedule a maintenance time where it isn't going to shut everything down. It's structured.
Yeah. We use the communications, the Ethernet, which we'll talk about in a minute, but we sell a lot of controllers that have a 4-channel recorder, and we can monitor through communications the resistance and record that and look over time the resistance, and actually the operating level at a furnace level is going to stay at like 40 or 50 degrees when they're operating, and we can tell over time that now if you need more, all of a sudden you're operating at 60% and your resistance is changing, you probably have an issue. And at some point you're going to get to 100% and you're going to need 120, and you're not going to have it because the heater just has lost its ability to generate power.
Yeah, to that point, you can look at the resistance, and it's going to tell you the health of the heating element. But you're also sensing and monitoring your output current. You're measuring temperature. There could be other things that are going on in the furnace, and it may not have anything to do with the heating element.
Right.
The door of the furnace is open.
Right.
The insulation is failing. So it gets back to that predictive maintenance and this digital technology. Within an SCR, that can give you all of that data so that you can have those structured shutdowns and you can make the necessary repairs.
Yeah, the size of the unit has enabled customers to use smaller packaging. The communications has enabled them not to need the meters on the top.
Right.
Because we have a remote display kind of like this that you can use on our controls that you can view the current, the amps, the voltage, resistance, all that, kW if you want. And then you can bring this data out digitally to the software or display it elsewhere.
That's a big thing. When you were asking earlier, what are some of the major improvements you've seen over the years, and then I said the digital technology, and we talked about the fusing. The other thing is the ability to gather this information right from an SCR. And a big one that people look at is power. They want to know power. Well, in the old analog style units, you had ammeters, you had voltmeters. If you wanted to know power, then you had to do it manually, calculate it by knowing what the current and the voltage is, or you could get a power meter. Now you have this multiplier that is in there, to take those current and voltages and make those calculations. Well, now you have this device. Now this SCR was this size. You put it in a cabinet. You got this meter, that meter. And now in today's digital technology, that's all built in. Right. And you're displaying that information over the network.
And you're also alarming on it. So you can now, I've been in places where the meter just goes like this, and like, well, what value is that? Well, if it goes like this or it goes like this, but you can set points around that stuff right now.
Yep.
And alarm on it. You can trend it and look at it over time from a diagnostic. One problem I've seen, I've gone in and troubleshot is, well, you're missing a leg. And a guy realized he had a fuse. One time, the guy didn't even have the fuse in. It was a startup, and he didn't put the fuse in the third, and you saw, oh, wait a minute, I got 240, 240, there should be a 240 there.
Yeah.
Right? So there's a lot of cool diagnostic stuff that goes with it.
Yeah, diagnostics is huge. As I said, one of the earlier on when we looked at it, used to be you had preventive maintenance. So there was a certain time we're going to shut the furnace down and we do this. Well, in the meantime, if you had a failure before that preventive maintenance period arises, now you got to shut the furnace down prematurely. The ability to look at all of those types of things that we've just discussed gives you the ability to say, okay, I'm starting to see a trend. I know we're going to have a problem. The next opportune time we can shut down. The digital technology gives you that capability. So now this box, SCR, as we've been talking about it, is now become an intelligent device. They can give you all of this and you can do a lot more with it in the terms of not only improving control, improving throughput, output, so forth, but now you can predict when potential problems are arising.
Okay. And we talked about communication. We have multiple communication protocols.
Yes. Yeah, today you'll have Ethernet IP, which is probably the most common in North America. Okay, and then you would have DeviceNet, which is typically in European. But you would have Ethernet IP, DeviceNet, Profibus, Profinet, Modbus TCP, and the newer one is EtherCAT, which is that's a lot in the semiconductor industry is where they use that.
Okay.
But all of those are available. Most people have those on those.
And we have software that connects via USB to it or read it via the Modbus over Ethernet to look at all the parameters? You can
look at the parameters. All of the parameters are now be available to you over any of those networks. Obviously, if you have that capability set in, you can do when you're setting digital units up. You set it up basically. It's like you're hooking it up to a computer, and you can set. Like in today's, we had talked about you want zero fired or phase fired. In the old analog units, you had to be specific, and they were two distinctly different units. In today's world, it's one unit. You change the software to change that firing angle. So you hook it up to a computer, and you have a software, and what you can do then is set the firing mode, set the limits that you want, voltage limits, current limits, a myriad of things that you can do.
Yeah. It's funny you say that because in the probably the late 80s, we sold an older SCR Robocon at the time. It was part of the Barbara Coleman, which company I worked for, and they had fixed transformers, right? One tap transformer. It was a 240 or 480 volt transformer, and a customer would say, "Oh, I need it. I ordered the wrong one," and you'd have to wait 8 weeks, right? And Control Concepts back then had a multi-tap transformer, and it didn't matter. It was sort of like digital. It's like, what do you want, 240 or 480? Just move the tap.
Yes.
And it basically brought their delivery down to, it was genius. It brought their delivery, and we basically became their rep and went from zero to a huge amount of SCRs because of that feature. When we could get it fast, and the reason we could get it fast is it had parts that lended itself toward getting, not stocking millions of things, getting inventory out.
Yeah, well, that capability now exists through digital technology that you can change that.
Right.
Yeah.
And I've done demos where I change from zero cross-phase amplifier to show people what it looks like.
Yeah, you have, a lot of them have, basically it's a universal input voltage. And you can run from 24 volts AC up to including 690 and anywhere in between. Yeah.
Okay. I want to go backwards before we go forward. So you've got a lot of experience. We didn't talk about what your journey looked like. We started with what company, and you're at Control Concepts. So where did you start?
I started with a company called Robicon.
The one I just threw under the bus.
Yes.
And that's how we met, actually, I think.
Yep. That's the part how we met, yes. And, Robicon was one of the first that I'm aware of to do SCR power controllers for the types of applications that we were talking about. And there were a few others at the time. It was Robicon, and then there was a company called Research Incorporated.
Oh, yes.
Okay, which the founders of Control Concepts, that's where they came from.
Yep.
The technology really was developed by Westinghouse, and that's where a number of engineers that worked at Westinghouse left Westinghouse and started Robicon. So that's a little history there. Yeah, from Robicon, I went through a number of things, and I went to a company called, it was, at the time, it was Eurotherm, okay, which, and in my relationship with them had occurred as a result of working for Robicon. Robicon was purchased by the Barber Coleman Company, which Barber Coleman then had purchased through various types of things, became part of Eurotherm. And then I worked for a company called Advanced Energy, AEG as it was referred to, which was a German company, and then to Control Concepts.
You got saved after AEG, and here you are at Control Concepts.
Yeah, here I am at Control Concepts. Thanks to I made a call to an old Barber Coleman friend of mine that put me in touch with a guy at Control Concepts.
I forgot that. You told me that you shared that with me a couple months ago. That that I called, because I do remember now. You were unemployed?
Yes, yeah. I was with Advanced Energy, and they had eliminated positions.
And I remember calling. Was Corey wasn't there yet, or was Stan?
Yeah, Corey was there.
I remember saying, you need to talk to this guy. He's a real good guy. I've known him for a long time, and here you are.
Here we are. Yeah.
Here you are, and you mentioned a company. I forgot. Research Incorporated. Back in the '80s, I was working for Barber Coleman, and I my wife was from Minnesota, and
okay.
I wanted to. We thought about moving out there, and I get the call. Research Incorporated was a temperature control company too. I mean,
yes.
they don't exist anymore.
Yeah.
But so I applied for a job at Research Incorporated in Minneapolis, and this woman called. Her name was Pam Vettel. Well, she sounded like my sister-in-law. Because to me at that time, I had only been married a couple of years. All Minnesota people sounded the same. So that she calls me, and I'm starting to have a conversation with her like she's my sister-in-law.
Yeah.
Right? I had no idea it was the company calling me for a job interview.
Yeah.
I ended up not even considering the job, because I remember September 15th, I went on an interview, Research Incorporated in Eden Prairie, and it snowed on the way. Now, it was just like flurries, but I went, I am not moving here. So
that's an interesting subject. Bring that up, because when I had talked to Corey, and he said, "Yeah, there's a potential opportunity," and he said in Minneapolis, in Minnesota, and so after we had our first conversation, I talked to my wife, and she said, "I'm willing to move south."
Yeah,
and we looked at the map and we said, "You know what? Here's Pittsburgh. Minneapolis is not."
No, it's not
south.
Not south. Although they've had really nice weather. It's been the 50s right now, and I don't want to. You don't like to time date a podcast, but it's February right now.
Yes.
So now let's fast forward, wrap it up. So right now we're hearing stuff with customers you got the Internet of Things, which we've addressed with communications to some extent, and that might get enhanced and all that. But one of the things we're hearing is things like a phase angle fired unit puts crap on the line,
Yes.
harmonics, and then at least over in Europe right now, power factor people are getting penalized for. Would you just talk a little bit about that whole piece and how people might solve it?
Sure. Power factor and harmonics has been around a long time. And as you said, when you're using phase angle firing, you're altering the sine wave. You're generating actually they're destructive harmonics. In addition to that, the power factor is changing. And when we talk about power factor, and to put it in the simplest terms, the power factor is the difference between the power that you require to come into the facility versus the actual amount of power that's actually doing the work. And the difference is the power factor. For an example, if you need 100 kilowatts of power and you're using phase angle control, you may need 110 kilovolt amps to do the work. So now you have a power factor of 0.9. And utilities look at that. If one of the old descriptions I can remember that people used to use is that you look at your phone. If you have a phone, cell phone, or even the old analog phones, you get a bill every month. If you do not use that phone, you make no calls or anything else, you still get that bill. Well, it's similar with the utility. The utility has to provide that power. It has to be available to you, even if you don't use it or if you don't use it the most efficient way. The difference of that is the power factor, and they will put a penalty on you. So, and that's negotiated. So you work at how are you going to get your power, and then what are you going to pay as a result of the penalty. If you're using it uniformly, meaning that the actual kilovolt amps entered in is what your actual kW load is, then you're fine. The difference then becomes the penalty. The other half of that, as you mentioned, is the harmonics. The harmonic content, and it's a little more difficult to quite understand. You can see power factor on your bill. You can't see power factor on your utility bill. However, if you're generating these destructive harmonics, they go back onto the main line, and they get put down, and they may go down the line to the neighbor. And just for an example, if you're running an industrial facility and you're generating these destructive harmonics, they can cause damage within your own facility, but you put it back on the line, and right next door is a hospital. Now, destructive harmonics, what they can do, they can mess up instrumentation, they can shut things down. You can't shut a hospital down. So what could happen to you, it's again, you're negotiating a power level and the way you're going to use the power. A power company can shut you down. So you're seeing more and more of it. And as we look at in North America in particular, right, which we are most familiar with, is that we have a relatively old grid, and we're adding more and more and more. So the utilities are being more and more stringent about these things. And you're going to continue to see it.
Mm-hmm. Okay. And if you don't see it, and you won't know until they knock on your door, or should they be checking their bills to make sure they're not getting nailed for it?
They should be checking their bill, and they're probably somebody's knocking on your door and saying, you agreed to this. If you don't do this,
so you have to fix it somehow.
You better fix it.
And we talked yesterday, I think the best way to fix a factory may not be individually, it may be at the pole.
It may be. You would definitely fix the problem at the individual device, but that could be extremely expensive.
And you'd need to fix it at every individual device.
Every
so if
individual
you've got 20
device.
furnaces,
Yeah.
It's expensive.
Yeah. And so what is required then is that if you're having that issue, the utility's coming, you're going to have to get an harmonic analysis. Mm-hmm. Somebody's going to come in and have to tell you what it is, and then you can look at things like power factor correction capacitors, or you get into power factor correction through these digital technology that you have, to correct it at the pole.
Okay. Sounds cheap. I don't think so.
It might be in relationship to being shut down,
or the bill or the surcharge you're going to have every month.
Surcharge, yes, yeah. It would be expensive because you'd have to have an analysis. You'd have to have people come in with the appropriate instrumentation, check it out, and then determine what you would need to do.
Okay. Cool. Is there? We're going to end here in a minute, but is there anything else you'd like to share that maybe we missed that you were up at 2:00 this morning thinking about?
Nothing that I can think of other than it's like it's really nice outside today. It'd be a good day for a bike ride.
Oh yeah, it's not that nice. Bike ride. I'm a 50. It's got to be 58 or higher. It's 30 right now. So awesome. Well, hey, it was awesome. You came up from Pennsylvania to be here for this. And a few customers, but for this primarily, that was the intent. I really appreciate that. And for more information on any of these products, you can contact us. There'll be a bumper at the end of this podcast for the contact information for me and the company. And by all means, if you have any questions or want to email us and ask questions, we can certainly get Dan to answer them. And thank you for spending time with us.
Thank you, Dominic. Enjoyed it.
Thank you.
Thank you for getting in the loop with us. We hope this podcast was informative, and if you need any assistance on anything in the thermal process industry, please feel free to reach out to us at 800-848-NETS. That's 800-848-6387. Or visit our website at www.nets-inc.com to fill out a request for information form. If there are any topics regarding thermal processes that you would like to hear on a future podcast, please send us a comment. We hope you have an awesome day every day.